So this is my experiment 4 on system stability analysis. In this experiment, I analyzed a system transfer function and determined its poles and zeros and examined how these affect the system stability and time response. So what I did in the first was I converted the given differential equation into Laplace domain to get the transfer function, and I applied Laplace transform and simplified the equation to get the transfer function. So this form actually allowed me to clearly identify the numerator and denominator, which are needed to find the zeros in the poles. In my case, I got 1, 0, and 3 poles. And then I plotted the poles and zeros on the complex plane. And here's my MATLAB sketch to verify. So there are poles at s equals 2 and 3, which are in the right half plane, which signifies that the system is unstable since it's in the right half plane. And because in control systems, even if one pole is in the right, it makes the whole system unstable. So I also analyzed multiple systems labeled G1 to 4, and G1 have complex poles showing the oscillatory behavior. G3 has poles in the left half plane, which is example of a stable system, and G4 is unstable because it has a pole on the right side. This one. So some challenges I encountered were again applying Laplace transforms correctly and also handling complex roots using the quadratic formula. I also found it challenging to interpret the pole zero plot and linking them to stability, also plotting them and verifying them in MATLAB. And my key takeaways are the pole locations actually determines the system stability. So LHP or left half plane is stable and right half plane is unstable. And imaginary axis is the oscillations, and as seen in the impulse responses, the poles directly affect how the system behaves over time.